Welcome everybody, and let's start talking about lecture 7 of sensitivity analysis. And the contents of this slide is from our handwritten handout, page 61 to 74. And it's called sensitivity analysis. Okay. And there are several changes could made for your linear program models. And first is you can change the cost factor, and you can change the right hand side of your resources, the availability to your resources, and also you might want to change some of the cost coefficient, the constraint coefficient in your A matrices. And also, you could add another decision variable or add another product or projects in your linear programming model. Also, you can add an additional constraint to your linear programming model. So this lecture just focus on how if some of these changes happens to your linear programming model. If this is possible, we don't have to resolve the linear programming model again, but using the current optimal tableau to figure out what are the changes to the optimal solution, the optimal tableau, and so on and so forth. All right, let's just start. And this part, the first part we are focused on is changes to cost vector C. The cost coefficient for xk for one of the x could change from ck to ck prom. If xk is not is a non-basic variable, then the reduced cost could be recalculated as following. Okay, I'm going to change the pen color a little bit. Okay, so if the cost change and the current xk is not a linear basic variable, then we can see that, and the c just changed to the original zj minus zk minus ck, and plus the changes between the cost ck to ck prom. So that's the new zj minus cj reduced cost portion. But if xk is a basic variable, then the problem becomes a little bit complicated, because the cb, remember, the z, actually, the zj minus cj portion equals to cb transpose times B inverse times AJ minus CJ. And if the CB changes, then actually all the ZJ minus CJ for all the non-basic column will change as well. So in this situation, what we do is we calculate the difference between the cost changes CB prom minus the original CB, and the difference is we call it delta CB. And then we can calculate the changes of ZJ to begin with, since the CB changes already. Okay, since this. So so Z prom changes, and Z prom changed, but C for non-basic column not changing. So we can calculate the original ZJ minus CJ, the new ZJ prom minus CJ, equals to, okay, here is the CB times YJ. And why is this? Because B times AJ equals to YJ. Okay. Equals to YJ right here. So that's what we're saying. Actually, the CB, the original, the non-changed part. So here what we say is for I to M, summation from I to M, but I not equals to T. T is the one who changed his cost coefficient. Then we adding that term CB prom, okay, CBT prom times YTJ, so it's that item change minus CJ. Okay, so we can basically say this part without the ZJ itself minus this term, which is the CBT terms times YJ, but plus this term, the new. So minus the original terms and then added to the CBT prom term, and that's what we have. So basically, we'll, after the calculation, we can see that this is equal to the original ZJ minus CJ plus the difference between CB and the CB prom and CBT, and then times YJ. So the major difference will be what? Delta BT times YTJ. So that's fairly straightforward. So if the CBT is changing, so CB is the corresponding XT is a basic variable, a slightly different result, a little bit more complicated because all the non-basic column will be affected by this CB prom. CB prom is the new ones, so actually should be Z prom right here. Okay, so next we see an example. So here is the new reduced cost, okay, equals to the old reduced cost and the differences. So let's take a look. So give example, maximize negative 2x1 plus minus 3x2 minus x3, subject to 1/3 of x1 plus 1/3 of x2 and plus 1/3 of x3 plus x4. x4 is the slack variable, equals to 1. Okay, and the next constraint will be 1/3 of x1 plus 4/3 of x2 plus 7/3 of x3 plus x5. x5 is another slack variable, equal to 3. And x1 to x5 are greater than equal to 0. Okay, analyze if C3 can be changed. So what we have, oh sorry, let me see if we can show the optimal tableau at this moment. The optimal tableau, we notice that, okay, all the ZJ minus CJ rows are negative, so we know this is currently optimal. And the right hand side, the objective function equal to negative A, and A1 equals to 1, A2 equals to 2. And this is our optimal tableau. We can see how well this change if C3 changes. Okay, so currently C3 is a non-basic column. Okay, so we can see C3 is a non-basic column. So if it's Z3 minus C3 originally equals to negative 3, okay, so Z3 equals to negative 4 equals to CB transpose times B inverse times A3 originally. So we can calculate CB transpose times B inverse. Where's the B inverse? Actually, we can easily identify since x4 and x5 are slack variable. So x4 and x5 are slack variable, okay, and at the slack variables down here, this is the B inverse. Okay, so also if C3 changed to C3 prom, C3 changed to C3 prom, okay, and then if this current tableau is going to maintain optimal, this thing's Z3 minus C3 has to be maintained negative. So here is Z equals to Z3 equals to negative 4. So the negative 4 minus C3 prime, it should be less than or equal to 0. So current tableau will maintain optimal. So that result, C3 prime has to be greater than or equals to negative 4. All right. So what if X3 C3 prime is equal to negative 5? So it's out of the range. So we're going to recalculate, okay, Z3 minus C3, okay, Z3 minus C3. We're going to recalculate Z3 minus C3, okay, plus C3 minus C3 prime. So here we minus C3, and here we added C3, and then we minus X3 right here. Okay, we'll go from this, so equals to negative 3 plus negative 1 minus negative 5, so equals to 1. So we know that right now the Z3 minus C3 becomes a positive. So what happened in the simplex tableau? In the simplex tableau, we notice that now X3 has a positive Z3 minus C3 prime. So this X3 can be entered as a basic variable. Okay, X3 can enter to the basis based on the minimum ratio test. X2 is leaving the basis. All right, so this is what happened if C3 changed to a degree, which making Z3 minus C3 prime becomes a positive number. Then we have to determine if we need to enter in this particular variable into the basis. And after pivot, we notice that all the Zj minus Cj elements are negative again, and the current objective function improved from a negative a to negative 9, and a1 and a3 are now basic variables. In that case, that's the optimal tableau. Next slide. Let's take a look. What if the right-hand side, B, is changing? So what if the B is changing from B to B prime? Okay, changing from B to B prime. I noticed that one thing we need to calculate during our process is calculate the current basic solution. The current basic solution equals to B inverse times B. Okay, if B changes, so should be B inverse times B prime if B changes. Okay, and also we want to check if the current Zj minus Cj still satisfy less than equal to 0, and XB prime, the new basic solution, is non-negative again, then we still have the optimal basic feasible solution. Okay, or if Zj minus Cj, we find, is less than equal to 0, but XB prime, one or more elements becomes negative, then we using a so-called do simplex method to find the new optimal basic feasible solution. So supposedly Bi, one of the B, changes from B to Bi prime equals to the original Bi plus the delta Bi is the change in the amount of changes. So right hand side equals to B prime equals to B plus delta B times EI. EI is the unit vector have 1 in the isolate position. So the basic solution becomes X prime B x prime b, okay, SB prime, sorry, equals to B inverse times B prime equals to B inverse times B plus delta BI times B inverse times EI. So basically, the changes amount of your current basic solution should be just delta BI times the column of the B inverse matrix. Okay, this is the amount of change we will have. If still currently the BI XB prime is still greater than equal to 0, still non-negative, then this delta B times the column of B inverse should be greater than negative XB. So let's look at the example. Same example we had it before. Okay. This is the current optimal tableau before the B right-hand side change. So the current B inverse, as recognized again, since x4 and x5 are basic are slack variable, and B inverse always happen in this area. Change color. Okay, and this is our due solution. Okay, omega. And currently A1, x1 and x2 are x1 equals to 1, x2 equals to 2. Okay, so we identify B inverse equals to 4, negative 1, negative 1, and 1. And right hand side is equals to, from the original problem, equals to 1 and 3. And we can study the range of a possible change for BI, okay, for one of the right-hand side. For example, if we just look at the B1, which is this 1, so going to change from 1 to some other value, what's going to happen? If B1 is going to change, so B inverse times B equals to B inverse times B1. If B2 is not changing, so see how much impact, how much range B1 could change. We want to maintain is greater, non-negative. So therefore, we have a two equation. 4 times B1 minus 3, negative 3, 3 times negative 1. So 4B1 minus 3 is non-negative. Also, from the second rows of this B inverse, negative B1 plus 3 is greater than equal to 0. So based on these together, okay, B1 should be between 3/4 and 3. Okay, B1 should be between 3/4 and 3. What if we only change B2 instead, and B1 hold on to 1, value of 1? And we can also calculate the value, okay, or the range of the B2 can change. It should be between 1 to 4. So we know that if B1 is maintained within 3/4 to 3, and this current tableau will not have still maintain its optimal. And also, if B2 changes, only one change. If B2 maintained between 1 to 4, the current tableau will also stay optimal. We just have to recalculate the XB, the B current basic solution. That's all. But what if B changes, B2 changes from, actually, let's do the previous one. B2 changes from current 3 to 5, and we see what happened. So right here, B1 stay with a 0, B2 change from 3 to 5. So B inverse times B prime equals to negative 1 and 4. So it's no longer maintain the non-negative constraint. So x1 actually at this moment becomes negative 1. Let's take a look at the simplex tableau right now. After that, changes, right hand side changes. So x1 becomes negative, x2 becomes 4. So we're going to apply do simplex method. Okay. So choosing the negative right hand side to begin with, and make sure all the zj minus cj are negative, non-positive. And then we're choosing a x1 as a leaving variable, and x5 based on the minimum ratio test. Here we have this row choosing the only negative one. So negative 1 divided by negative 1. Here what we have for x3, we have negative 3 divided by negative 1 will be 3. And choosing the minimal one, and that will be x5 is entering. And after pivot, making x5 an identity column, and then we have a new basic solution, okay, x3 enter, okay, x5 enter, and x2 also maintain basis, x5 equals to 1, x2 equal to 3 in this case. So this is a situation because it looks like the changing over right hand side is slightly easier to deal with because they only impact the current basic solution. Okay, if the current basic solution maintains non-negative, then the current tableau is still optimal. If the current basic solution becomes negative, in that case we probably need to do a do simplex method iteration to make this infeasible primal solution back to feasible. Okay, that's a new optimal tableau in that case.